So a context-free grammar consists of 4 parts. The first one is the terminal letters, which can be regarded as the letters in this language. And then the second one, N, is the non-terminal letters. And then we need a production. We need some rules to produce this language, which consists of one letter in the non-terminal part, and the other part consists of the terminal letters and non-terminal letters. And then we need a start non-terminal, which means we start from this S and then using these rules to produce some languages or set of letters. And the language of this rule, the language generated by this rule is called a context-free language. So let me give you an example to show what they are. So for example, the terminal letters are A and B, and the non-terminal letter is just one simple one, S. And then the rules consists of S and A as B, and S and an empty set, and an empty element. And then we start from S. And the production can be written as we maps S to A as B or S to nothing. So let's talk about what the language should be. So we start from S, an empty set. And then the next step is we can generate an empty thing. Or if we use this rule once, the first rule once and the second rule once, when we get a letter A, B. If we use the first rule twice and then the second rule, then we get A, B, B. So to summarize, using this grammar, we will get a rule like A to the N and B to the N, where N is a natural number. So A to the N, B to the N can be regarded as a context-free language. And then we can see the connection between this context-free language and the number theory, the group theory. So there are 2 theorems. The first one tells us that the word problem of, the word problem of a group is context-free if and only if the group itself is virtually free. The second theorem tells us the multiplication table of a group is context-free if and only if it is hyperbolic. So using these 2 theorems, we can tell whether a group is virtually free or hyperbolic by thinking about the word problem or the multiplication table of it. Another famous thing is the pumping lemma of this context-free language. So if the language is context-free, then for any letter in this language, we can do this pumping rule, in which we cut this word. For any word, we can cut it into 5 parts, and then we can pump it with the second and fourth letter. Using this rule, we can show that some languages are not context-free. For example, here, we have just shown that the language A to the N, B to the N is context-free by defining the grammar. But here, we will using this pumping lemma to show that this language is not context-free. because we cannot, using this lemma, we cannot find out a proper v and a proper y to pump this this word. For example, if we choose v as A and Y as B or C, then we cannot, then the power by doing this pumping, the power of A and B or C will increase, but the power of the other letter will keep the same. If we choose V or Y to be a part of this word which contains more than 2 letters, say it's AB or BC or some ABC, then we cannot do this pumping, because if we use AB, then we will get A. Let me write down something. Then we will get A to K, and then we get AB, B to something. If we pump this part, we will get A, B, A, B. When n equals 2, then it is no longer in this language, because in this language, we do not have ABA or BAB like this. So this pumping lemma can be used to show that some language is not context-free. And then let's talk about the multiple context-free languages. So in the context-free language, we can regard a rule. The rules are like this. We start from a non-terminal letter and then maps to a word which consists of terminal letters and non-terminal letters like this. We can regard this rule as, we can regard A as a function. All the non-terminal words as a function, and we can regard the terminal words as values or something. And then we can translate this rule into here. So we regard A and B, A and B1, B2 up to Bn as a function. Then the variables should be like in the similar form, like W1, which is a value, and X1 is the variable for B1, and X2 is a variable for B2, and so on and so forth. If we translate this rule into this way, into this form, then there is a very natural generalization, which means that all these functions are not necessary to be one variable. There can be multiple variables for each function, and that is the generalization for multiple context-free grammar. Let's show this. So if there are more than one variable, then A can be written like in this way, and B. So for example, there are K1 variables for B1 and K2 variables for B2 and Kn variables for Bn. And the variables for A, they are just strings of terminals and some variables like X, Ij, which are the variables of B1 up to Bn. And there is some resistance, there are some condition for these variables. For all the Xij in Si up to Sm, the variables should be different. Xij should be different from each other, and they can be used only once in the variables of A. And in this definition, we call Ki the rank of the non-terminal Bi, which means the numbers of variables for each function is the rank of that non-terminal. And to produce a rule, we also need another rule, that can be regarded as the start rule of this construction. We start from nothing and we just construct the function, and all the variables are just empty. Let me give you an example to show what's they are like. So say the non-terminal B1 use two variables that are x and z, and the non-terminal B2 use two variables v and y. Then we can define a rule which is noted as s. S only need one variable. You can use two or one, but I mean here we just define one variable. And it is not necessary to use all these variables. We can just ignore some. So here we just pick out x and y, these two variables, or from B1 and B2. And then we get a new variable, which is a, x, b, y, c. And a, b, c are in the terminal letters. So let's start this example. So in this example, we start from nothing and we define our non-terminal letter t, which uses four variables. So at the very beginning, they are just empty. And then the second rule is from t. So t, x1, x2, x3, x4 can be mapped to t, a, x1, b, x2, c, x3, d, x4, which means that we just multiply, we just put a, b, c, d, which are the terminal letters, into this variable. And then the last rule is from t to s, we just combine these four variables. And then s is the final result. So using this rule, we will produce this language. Say we start from nothing, and using this rule, using the second rule, we can get t. If we use the second rule once, we can get t, a, b, c, d. If we stop using the second rule and can get into the last rule, we will get s. We just multiply them up, and the final one is a, b, c, d. And if we use the second rule twice, then we will get a squared, b squared, c squared, d squared. Also, if we use it n times, then we will get a to the n, b to the a, c to the n, d to the n, this language. There is another example. So if we start from nothing, and then we define p and q, and p is, we need two variables for p and two variables for q, and we multiply by, we just put a and c on the left of x1 and x2, and then b and d on the left on the x1 and x2 here. There are two rules. The last rule is just to multiply them up. And in this way, we will define a language which consists also a, b, c, d, but the power of a and c are the same, and the power of b and d are the same. So that is another example about how to define a multiple context-free language. I'm done. So the next problem is how to this is the definition of the multiple context-free language. The context-free language can be regarded as a one multiple context-free language because all the terminals consist of one variable. The maximum rank is the number before the multiple context-free language. If all the variable, if all the rank of the non-terminals are k, then we can define it as k multiple context free. If some of them are 1, some of them 2, and some of them are n, then we will define it as n multiple context free. Then let's get back to the word problem. So one famous result about multiple context free is this one. So the word problem of z square is 2 multiple context free. As we talked about before, the word problem of a group is it's context free if and only if the group is virtually it's virtually free, but certainly z square is not virtually free. But I mean, we can prove that the word problem of this group is 2 multiple context free. And then the next result is that the word problem of z to the n is also multiple context free, but unfortunately it's not n multiple context free. We need a function like this. And certainly for n equals 2, the result is weaker than the first result, but it's a more general case, which means that the word problem of z to the n is multiple context free. And then let's talk about how to show a language is not multiple context free. There are several different methods. So the first idea is to use the pumping lemma we talked about before. So there is a definition called finite pumpable. So we call a language finite pumpable if we can, for any word in this language, we can cut it into 2k pieces. Oh, here we need 2k plus 1 pieces. And we can just pump the u part. So the pumping lemma we talk about for context-free language shows that the context-free language, which can also be regarded as one multiple context-free language, can be is finitely pumpable. And in this case, we only need 5 parts of the word, so k is 2. Unfortunately, it is not true for multiple context-free language. Kanazawa has shown that for m greater than 3, we can always find some multiple context-free language which cannot be finitely pumped, which means that we cannot carry on the old pattern of the pumping lemma to figure out a generalized pumping lemma for the multiple context-free language. And then there are several different ways to solve this problem. The first one is pump the language with one word. So Saki has shown that for any k multiple context-free language, we cannot pump every word, but we can at least choose one word. There exists one word which can be cut into 2k plus 1 part, and we can use this 2k plus 1 part to pump this language. So all the word of this form, which is to pump w using u1, u2 up to u2k to pump this. All this word is in this language. So let's talk about the difference between these two things. The original pumping lemma tells us any word can do this pump. Any word can do this pumping, but Saki told us that we cannot do this, but there exists at least one word to pump this language. And using this pumping lemma, we can show that this language is not K multiple context free. The proof is kind of complicated, but I mean, I don't think I have enough time to talk about the proof. But we can do this using this one-word pumpable lemma. And then our job is to do another way. So roughly speaking, instead of pumping it, we use some part to swap this U part. So for any word W, as long for any long enough for W, we can cut it into, here I used MI, 2MI part. And we can, instead of pumping it, use some power. We can swap U1 up to UMI with something else. So we define the big U. So big U, big U's are just some set consist of different letters. We can do this swapping to show that every word W in this language, which is long enough, we can cut it into several parts, and then we can do some swapping. And for any swap, so for any words generalized by this swapping, the new word is in this language. So the difference between our lemma and the original pumping lemma is, in the original pumping lemma, we just pump U1 up to UK by a power of n. But in our theorem, instead of pumping it, which has been shown impossible, we just swap these U's with some other things, and this swapping does not depend on this word. We define this swap. We define this big U set before this choosing this word, and then we can also prove that this language is not K multiple context free by using this theorem. Also, using this theorem, we can have another theorem that is we call the gap lemma, which means that if you're given a infinite language L and the corresponding alphabet sigma, we can define the length of each word in this language. If there exists a gap between the words in this language, so for two words which are long enough, then the difference between the lengths is large enough. Then we can show that the gap of the length in this language is greater and greater with the length increase. Then this language cannot be multiple context free. And using this gap lemma, we can show the following languages are not multiple context free. So the language like this or this, because the power on the top increase, it's greater. I mean, it increased faster than linear. So the gap will be greater and greater with the length increase. So we can using this gap lemma to show that all these languages are not multiple context free. Yeah, that is the end. Thank you. Do you have any question?
Thank you, Mengfan, for a nice talk. Does anybody have any questions? For the class of, like, let's say, unambiguous multiple context-free languages, are there any results about generating functions that are known? Like, maybe not, maybe there's nothing known about like how complicated there are, but is there anything unknown about what sort of like functional equations, like a generating function of an unambiguous multiple context-free language would have to satisfy?
I'm not sure about that. Mari, do you have any idea about this?
No, the worst I can think of is the word problem of z squared at the moment, but there's nastier languages that are multiple context free. I can't think.
Yeah, maybe it's just so horrible that no one studied it
Yeah,
or something.
definitely not.
Well, if no one else has any questions, then thank Mengfan again.
Thank you.
Thanks.